But for tonight's special lecture, we're really delighted to welcome Dr. Jillian Scudder, Professor of Physics and Astronomy at Oberlin College. I think I first invited Jillian to come down and visit about 3 years ago because my daughter was a student at Oberlin. She's a drummer, so no physics, no astronomy, but I thought, oh, Oberlin must have astronomers. And I kind of looked up and I said, oh, I know who she is. And she should come down. And at the time, Jillian was away on sabbatical, so it kind of didn't happen then. But I knew Jillian because of her work on galaxies and understanding the relation between chemical elements and star formation and mergers of galaxies. And I was kind of blithely unaware that she also has written 4 books. Maybe it was 3 at the time, but now it's 4, and has a huge presence in radio, public lectures, and so forth. So it was a terrific opportunity to get her to come down for our public lecture, and she is also going to be visiting the astronomy department tomorrow. And Jillian grew up in Florida, but decided she wanted some cold, so moved to Minnesota for college at Macalester, and then decided that wasn't far north enough, so went to University of Victoria, where she did her PhD. And started working on the abundances of metals in galaxies. And then moved to the University of Sussex in England and spent 3 years there as a postdoctoral fellow before moving back to the US to her faculty position at Oberlin College. And she has been there ever since. And on the table in the back, you can get at least 2 of her books, and after the lecture, she'll be available to after the lecture and your questions. Then she'll be available to sign books and other things. So please join me in welcoming Jillian Scudder.
Well, thank you all for the kind introduction and for coming. I am going to be telling you a series of stories that sound silly but are true about outer space generally. And so contractually, I am required to tell you that these are coming from my book, The Milky Way Smells of Rum and Raspberries. And so the stories that I have for you today, plus some 30-odd other stories of similar nonsense, and more footnotes than I can include in a series of slides, are contained in here. So we should get oriented. So this is where we are in our solar system. This is a roughly true color in terms of eyeball color, if you were to go looking at it. Visualization of the solar system, where the planets are to scale in size, but the distances between those planets are very outrageously not to scale. Because if we were that close to the sun, we would die. So we are sensitive button press. There we go. We are here. We're the 3rd one out. We have Mercury, Venus. Earth is the only nice one out of the lot. Everything else in the solar system is absolutely horrendous tourist vacations. Would not recommend a single other place to be. So there are lots of things I could tell you about all of these different planets, but the thing I'm going to start with is talking about Neptune, because Neptune is weird and interesting, and we have only been by it 1 time. So Neptune looks like this most of the time. This is the most distant major planet in our solar system. This is probably the most famous image we have of it, and the things that we can see right away is that it's very bright blue. There's some white clouds, and that's what we've got. This image was taken by Voyager 2 in 1989. That was the only time we have gone past Neptune. We have not gone past it since. So this is the most up-to-date image we have of Neptune from close up. And this makes a lot of planetary scientists very sad because it is an interesting planet and very weird. One of the first things that I need to tell you about is that this image is an accidental lie. Neptune is not this color. This is an exaggerated color image. It was known to be an exaggerated color image in 1989 when it was put out, and since 1989, the sense of exaggerated color for this image has been slightly lost. So Neptune is actually this color. It's much more like Uranus in color. It's a paler blue. The reason it's often visualized in this darker blue is that the color differences are more obvious. So you can see like, oh yeah, there is this really, really dark blue and then really, really bright white. This is the same image. You still have the same number of clouds. It's just not as dynamic, and the blue one is kind of prettier, and so it gets circulated a lot more. But it's still blue, and the blue comes from methane, and methane is a little molecule we're going to talk a lot more about. But the function of methane in this particular context is that it absorbs red light, and so then it reflects the blue light, and we wind up with this blue color. The white clouds are usually ammonia or water or something along those lines, which are reflecting just all of the light back. If we think about Neptune in comparison to the Earth, this is again to size scale, but not to distance scale, because otherwise we'd be in trouble. Neptune is 4 times the physical size of the Earth, but 17 times the mass. So we have packed the material quite densely into Neptune in a way that we have not done on the Earth. The Earth is cheating slightly because it is made out of rock and metal, and so there is an intrinsic density there. But rock and metal don't like to compress very much, and so it's kind of hard to make a rocky planet any more dense than the density of rock and metal. It doesn't squish. Meanwhile, Neptune is made out of things, 80% things that we would consider ice on Earth. So these are things like water, ammonia, other methanes, just at really, really high pressure. And these things are gases, and so those can actually be squished to very high densities. And so that's how we get this 4 times the size, but 17 times the mass. We learned, considering that Voyager just did a speedy swing past Neptune and did not stop to orbit Neptune at all, it just went past, took a lot of pictures, took a lot of data, and then just zoomed straight on out of the solar system. The fact that we know so much about Neptune is kind of impressive. Other things that we learned is that Neptune has the highest winds in the solar system at something like 400 plus miles an hour. So if you are looking in the upper atmosphere of Neptune, the clouds and the gas that Neptune is made up of are moving incredibly, incredibly fast. And one more thing that we know about Neptune is that it's a little bit warmer than we expect that it should be. So if we look at Neptune and we go, okay, well, it's really far from the sun, which should not be getting a lot of sunlight to warm the planet. There's a balance that we can imagine of when we've got sunlight coming in, it's reflecting so much light, the rest of it has to be absorbed, so it should be about this temperature, and it's a little bit warmer than that. So there is something happening inside Neptune that is heating it up somehow. So this is interesting already. So these are things that we know just to be like, okay, Neptune, slightly puzzling planet, it's blue, it's very far from us, it's warmer than it should be. But we have never sent any craft to go stay around it. So just to give you a sense of what we have been able to do from where we are, this is our blue version of Neptune from Voyager 2 in 1989. Since then, we do have a few more images of Neptune. This one is from Hubble, the space-based telescope that's in orbit around the Earth from 2021. Distinctly fuzzier. That would be because that Hubble is not immediately next to Neptune. So we're doing this from Earth. Hubble is a very wonderful telescope. It's very large, but it can only do so much. Even more recently than that, we have this JWST image from 2022, where JWST is looking at the temperature of the planet. And so these bright spots are areas that are warmer, and the cooler spots are areas that are cooler. You can also see the rings very dramatically in the JWST image that we could not see in the Hubble. That's because they're very thin and not very bright. in terms of being reflective. We can see some moons in there. And what we can't see, except there's a faint haze going vertically, is that there is another moon, Triton, just out of scene, which is very, very bright and casting some glare into our image. So this is kind of what we've got to work with from Neptune. We don't have a lot of really high resolution images of it. We have the ones from 1989 when Voyager went swinging past. And then after that, we have done our best, but there are fundamental limitations to how good our imagery can get. So we are not actually able to just take really, really high resolution pictures of Neptune and then go, what's happening? So we have a problem, which is that we still want to know what's happening inside of Neptune, but we are not going to be able to do it from here. So we still want to know how this works. So we're going to have to figure it out from here, which is a challenge because Neptune, as far as we can tell, is very, very little like the Earth. So it's not made of the same things. It's much more dense. It's bigger. It's in a very distant outer solar system. We're going to still want to figure out why it is doing the things it's doing. So this is the part of the talk where I get to show you a whole bunch of industrial safety hazard signs. So, things that Neptune is made out of. Methane. If you breathe it, you will die, and it catches on fire. So this is our two hazards here. It is flammable and explosive, and if you breathe it, it's bad times. Don't recommend it. If you are dealing with ammonia, which is also part of the cloud layers of Neptune, you can use that as a cleaner, but please never under any circumstances mix it with bleach, because it will kill you. It will make chlorine gas, which is not good for you. Ammonia itself is also toxic and corrosive, so you need to be super careful with it, even if you are using it as a cleaner, nowhere near the vicinity of bleach. And so we have a problem of we're dealing with a planet that is made of things that kill us in densities that are really bad for us from the other end of the solar system. And this is our challenge. And yet, we have a model of what the inside of Neptune looks like. This is one of my favorite diagrams in the world because we have Neptune at the top, and then we have our little slice of wedge in the middle that tells us what this is doing. So at the very center, we think there's probably some rock, not a lot, but a little. At the top, we have our upper atmosphere. That's the part we're seeing in our images, and that's our mostly hydrogen and helium. And then we have these two layers that say formation and precipitation of diamonds, and then diamond layer question mark. Where we have diamonds raining out of the skies of Neptune and then collecting potentially somewhere deep inside Neptune. So we have made the statement that Neptune rains diamonds, and now we have a pretty reasonable follow-up question, which is how did we get to that conclusion when Neptune is on the other end of the solar system and we have not visited for more than a couple of minutes at any point in the past? So we, to understand this, need to understand methane a little bit more. So methane is a molecule of a class called a hydrocarbon. Hydrocarbon just means that it is made up of hydrogen and carbon and nothing else. So all of our hydrocarbons will look like carbon and then it's surrounded by a series of hydrogens. Methane looks like this, so it's one carbon, 4 hydrogens. You can also write it as CH4, that's your chemistry notation, or you can draw it out three-dimensionally because it's actually kind of a pyramid shape, but that's hard to draw and it gets convoluted the more your molecule gets bigger. So I'm going to stick with the flat lay version where we smashed it down and pretended that it was intended to be flat. So hydrocarbons have this fun property where you can just kind of keep stacking them together. And so you can start with methane, and then if you add another carbon, you get ethane, which is 2 carbons and more hydrogen. And then if you keep going, you can make propane. which we use for stoves. You can make butane, which you use for torches. And if you keep going, you get nonane, which I've stopped because that's as big as it fits on the slide. Anything larger than that, I would have had to shrink the molecule. But you can just keep going. And these are your basic hydrocarbons. It's just a pile of carbon and then hydrogen everywhere else. And most of them are flammable. Which is why we use propane stoves. It's why we use butane torches. It's why all of these things are not great to have in a lab, because our operation at the moment is that we would not like to set our lab on fire, but if we're going to pretend to be Neptune, we need to make our pretend Neptune be at high temperature and high pressure. And if you put your Neptune gases at high temperature and high pressure, what they are going to want to do is catch on fire. And so we don't want that. Most of our labs have this kind of signage in them. Do not smoke near the lab. We don't want the smoke coming from inside the lab either. So we now have a problem. And so did the scientists trying to understand Neptune, which is that we have a do not set the research lab on fire challenge while simultaneously understanding Neptune. So we need to not use methane or propane or any of these other very, very flammable materials, but we do want to work with a hydrocarbon. So we need a new material, and we're going to have 3 things that we need it to do. 1, we would like it to be made out of hydrogen and carbon, and that's it, because we still want it to be a hydrocarbon like what Neptune is made out of. We would like it to not catch the lab on fire, just for health and safety reasons, and also nobody wants to deal with the insurance. And ideally, we would like it to be cheap, because that's always nice if your lab experiments can be cheap. It just makes your life easier. The fabulous news is that we have a material that we have all worked with that meets these criteria, and it is Styrofoam. Which, as we know, is not extremely flammable or incredibly toxic, or we wouldn't use it as packing material. So we've got 1 out of 3 already. It's also real cheap, or we wouldn't use it as packing material. So we've got 2 out of 3 already. The thing that we need to check on is the hydrocarbon status. Is it made out of hydrogen and carbon? And it is. So styrene, the base molecule that goes into polystyrene, which is the formal name for styrofoam, is this. And that is more carbons than our methanes and our propanes and our butanes, but it is nonetheless just carbon molecules and hydrogens. And then once you stack it together to make polystyrene, which is just a string of them, you still only have carbon and hydrogen. So our 3rd criterion, that it has to be made out of hydrogen and carbon, is also a go. We have a material that does the things that we want it to do. We are going to use Styrofoam to understand Neptune, because it does all the things that we said we needed. So we've got our check marks. It's made out of the right things. It's not flammable. It's not toxic. It's cheap. Easy to get. The challenge now is that we need to pretend that Neptune is Styrofoam, or we need to pretend that Styrofoam is Neptune. These 2 things are not the same. Largely, Styrofoam is notoriously low density and light, or we wouldn't use it for packing material. And Neptune, as we said at the start, is very dense. So we need to do something to our Styrofoam to compress it, to make it pretend to be Neptune more effectively. And now we get to introduce a high-powered laser. Our high-powered laser, as with all lasers, you should not point at your eyes, is going to do 2 things. Its job is to heat and to pressurize the Styrofoam. So what it's going to do is you're going to shoot this laser at a material, and if you have a high enough powered laser, your standard laser pointer, this kind of thing, will not do that. But if you have a high enough powered laser, it will heat the thing that it hits. So the heat and pressure that the laser is going to introduce is going to be what gets us to pretending to be Neptune's atmosphere more effectively. So we're going to take our laser, we're going to shoot it at some styrofoam. If we have a high enough powered laser, it will superheat the material. And when we point it at styrofoam, what it's going to do is create an explosion at the surface of the styrofoam. That styrofoam explosion will move outwards through the styrofoam and create this shock wave of high temperature and high pressure. Doesn't last very long, but it is a shock wave nonetheless. It just has to be there for a little bit of time. This will give us a high pressure region in styrofoam. At this point in our experiment, what we have done is exploded some styrofoam. That is all that we have happened right now. What we are trying to do is to see if we can compress styrofoam hard enough. What you are trying to do is break apart all of the molecules, or break apart the molecule into individual atoms and see what happens. So our goal with this is to take our polystyrene and throw it into a pile of carbon and another pile of hydrogen and just completely break apart the molecular structure that we had. And if we do that, then what we are doing is say, okay, now I have loose carbon because I've broken all of my molecular bonds and I have it at high pressure and high temperature. If I'm going to take loose carbon at high temperature and high pressure, that is a great way to make a crystal. This is how we do lab-grown diamonds. We throw carbon into a region of high temperature and high pressure, and we wait for it to crystallize. And so the question was, hey, if I shine a high-powered laser at styrofoam and explode it very slightly for very short periods of time, do I make tiny diamonds? And they did. It made nanoscale diamonds, nanometer-sized diamonds, really tiny diamonds, but the laser was only on for a short period of time. So they managed to take a laser and some styrofoam, replicate the temperatures and pressures of Neptune, and then watch diamonds fall out. And so the conclusion was, if we can make tiny diamonds by exploding styrofoam for tiny fractions of a second on Earth in a lab, then there's really nothing saying that Neptune can't be doing this all the time because it just exists at high temperature and high pressure. It's got a whole bunch of methane hanging around. So if it exists at high temperature and pressure, like what the laser could do for us, then we should be breaking apart methane inside of Neptune. And then with enough methane, we can steal all those carbon atoms and compress them down into a diamond. And then you have diamonds forming in the skies of Neptune. And then once you have diamonds forming in the skies of Neptune, you have diamond, which is now a rock, in the sky, which is not rock. And so at that point, it should fall. And it will fall downwards, which is where you get this formation and precipitation of diamond and the diamond layer at the bottom, because it has to stop somewhere. So it should sink. That gives us the diamond rain. You can think about anything as raining as long as it's falling through something that's less dense than itself. And so that is pretty cool. We got to that from exploding styrofoam, which is a pretty cool experimental result. Like, hey, I can't make my lab explode. Let's do it with styrofoam and a high-powered laser. Oh, we made diamonds come out of styrofoam. And also that's Neptune. So this sounds cool, but in practice, this is what I would consider to be terrible. It sounds really neat. On the other hand, I need to remind you that one of the things that we said at the start was that Neptune has the fastest winds in the solar system. And if you need to sandpaper something that aggressively does not want to be sandpapered, you do it with diamond. And so this tells me that Neptune is an industrial abrasive. And therefore, it is sandpapering itself warm inside itself. So this diamond rain is genuinely the theory for why Neptune is slightly warmer than we think it should be, is because it has diamonds falling through its own atmosphere, and then the friction of throwing diamonds downwards through this whole atmosphere is heating itself up. So it is genuinely abrading itself warm on the inside after forming diamonds in its own sky. Space is fun. Remember how I said everywhere else was a bad tourist destination? It's true, and it will continue being true. So let's do another one. Now we can raise the stellar dead. We're going to be necromancers real quick. So in order to do that, I have to tell you what it means to be stellar alive. So stellar alive is, if you are a star, we consider you to be alive when you have in your core the ability to take hydrogen, our simplest atom, and convert it into helium through fusion. And so if you are a star, you have this balancing act between fusion, which is generating a huge amount of energy in the core of your star, pushing outwards, and gravity, which is because the star is quite massive, pulling inwards. And these two things exist in exact balance for most of a star's lifetime. And so you have this fusion pressure outwards, you have gravity pushing inwards, and they balance each other. If you are going to do this, you need to have your core at about 10 million degrees, slightly more than 10 million degrees, but it's really hot in the core of these stars. And you need to have a lot of very densely packed material. You have to get atoms very close to each other or it's just not going to happen. So you need to have really, really high temperatures, really, really high pressures. So when you start a star, most of the time, they're mostly hydrogen. So having a lot of hydrogen around in the core, not a problem. And having that, being able to crush it down will just happen from gravity. And so once you have gravity crush your star down, and you have lots of hydrogen around, you can smush the hydrogen atoms together and you can start fusion. And then you have an alive star. If we are something like our own sun, our star's been doing this for about 4.5 billion years. We have another 4 billion years before we start to change anything for our own sun. But there is an end to this process, which is that you can only have this alive state of hydrogen converting into helium so long as you have a lot of free hydrogen in the core. If you let this go long enough, then the hydrogen that was there will have all been turned into helium. And now we have not so much free hydrogen because we have piled up a whole bunch of helium instead. So what happens when it runs out? Well, now we have reached the end of life of a star. So again, we have this fusion balance. So we have the core, which is creating this pressure outwards from fusion, and gravity pulling you inwards in all directions. When you run out of fusion materials, then the balance is thrown off. And so you suddenly no longer have fusion pressure outwards, but you still have gravity. So gravity is going to push you inwards. And what that's going to do is compress the core even more. And you're going to be able to start turning helium into heavier elements. And outside of that region, you're going to start, very briefly afterwards, you're going to start creating hydrogen fusion in a shell around the core. And what happens is, this doesn't last very long, because now I have two sources of outward pressure, and gravity is still just the same old gravity. What this does is it's able to push away the outer layers of the star and leave behind just the core, which was too dense to expel. So this is the future for our own star. From here, in this process, there are two possible end paths. If the core was is able to support itself against gravity, which happens if it's lower in mass, so stars like our sun or less massive, then it will just hold on and gradually fade in brightness. And if it can't, it will catastrophically collapse inwards on itself. So for the sun, the end path is this fading. It will lose its outer layers in this sort of gentler process, and it will become an object known as a white dwarf. If you have a much more massive star, the process of losing your outer layers and the helium fusion, it goes on a little bit more complex and a little bit longer, but you still at some point have an end state of the core. And in a much more massive star, we'll try that one again, you will wind up with a catastrophic collapse, and then you have a black hole, which is tiny. If you're comparing the size of a black hole to the size of a white dwarf, they can be of similar sizes, but the white dwarfs tend to be much smaller in mass. So you have usually, if we had similar-ish sizes of stars, you have a really small black hole and still a pretty small white dwarf. So these are two kinds of stellar dead. We have black holes, we have white dwarfs, there's also neutron stars. I haven't talked about them. But these are the two that I'm interested in here. Neither of these are fusing anything. So technically, they are both deceased in terms of our sense of what it means to be alive. And so they are formally known as a stellar remnant. But I said we were going to raise the stellar dead, so we have to go raise them and figure out a way to make them fuse again. All right, so if you are a star, it is very likely that you will be found near another star. And so our sun is kind of unusual in that it only exists by itself, but many stars have companions. And they will orbit each other and go through their ends of lives together. And you can, as a result, wind up with a white dwarf orbiting a black hole after some very long period of time. This will stay like that for a long time. They'll just orbit each other for a really, really long time. And for the general vast majority of time, it's just going to hang out. You'll see a white dwarf orbiting something basically invisible, and it will just continue to orbit. But if you leave it long enough, they will slowly lose energy and fall towards each other. So because that's going to take a lot of billions of years, we're going to skip ahead to when the interesting things happen and zoom in. It's the same clip art. But we're going to zoom in and say, okay, they're closer now. The black hole is going to be able to do a magic trick and make the white dwarf start fusing elements again. So gravity in this situation is going to be pulling the two objects together. When you have a massive object next to something that has some physical scale to it, so physical size, you wind up with a tidal force, where the gravitational force on the near side of your object is stronger than the gravitational force on the far side. And what winds up happening is you stretch your object out into this long, flat shape. And then the near side is even nearer and gets an even stronger gravitational force. And so you stretch it out even more. And then you can keep going until at some point you have compressed the middle of what was your white dwarf enough that it can start fusing very, very briefly. So that turns our black hole into a necromancer because it has now raised to stellar dead. The white dwarf is having the worst day of its life. So now we have outward pressure because we have fusion again. But we're not in a spherical object anymore. So the pressure outwards is going to destroy this white dwarf. So we have fusion happening very, very briefly. There is an out path that is easier than the other paths, which is perpendicular to the direction of stretching. And that's where your explosion's going to go. So you started fusion, it's going to explode vertically. The rest of the white dwarf, however, is just being turned into a noodle. So this only happens kind of in the middle of your white dwarf. The rest of it is just noodle time. There is a really fun term in astrophysics, which is that when you stretch something out into enough of a noodle around a black hole, it is called spaghettification, which is where you turn it into the shape of a spaghetti noodle, cooked, apparently. So whatever didn't self-destruct in this 10 seconds of fusion that it can sustain is going to be completely shredded into a huge noodle, which does not bother the black hole at all, but has ruined the white dwarf completely. So you can only do this one time in your system. Once you shred the white dwarf, you're done. That's it. It is not going to restart fusion again. It is just going to be gradually consumed by the black hole. And that is what has happened there. Rest in many, many, many pieces. All right, I have one more for you, which is not so long. I'll give you the punchline at the start. Do not drink the gas at the center of the Milky Way, even though it smells delicious. So this is maybe no surprise, considering that everything I've told you so far today has been that space is awful and it will try to kill you. This is no exception. So I will show you the Milky Way as a whole. This is an image from the Gaia Space Telescope showing the density of stars in the Milky Way. And so we can see from our perspective, there is this band of bright material through the middle. That is the disk of our galaxy. There's a bunch of dust there. There's more stars behind that. We just can't see it. There's stuff blocking the way. We have at the bottom the small and large Magellanic Clouds. Those are things you could see if you visit the southern hemisphere, but they're not visible from our northern hemispheric perspective. And so this is what our galaxy looks like. If we zoom in a lot, this is just a very fun visualization where if we take a whole string of images from different telescopes looking at the center of the Milky Way, we can compile a string of images showing what it's like to zoom in on the core of our galaxy, where we will see increasingly just more and more and more stars. And at some point, we will switch images. There we go. And we can keep zooming in until we get to some point of going, okay, that's the center of our Milky Way. And that's, oh wait, there's more. We switched images again. So this is the center of our Milky Way. There is a lot of scale happening here. Each one of these stars is its own star in its own right. So we have zoomed past some 100 million, 100 billion stars to get to this subset of them. So we've zoomed in slightly too far. I am going to point us a little bit step back, but looking at the center of our galaxy, we know that at the very, very center, there is an object called a supermassive black hole, which is very much like a black hole that we were just talking about, except supermassive, because astronomers are great at naming things. So, supermassive black hole, they live at the centers of all galaxies as far as we can tell. This thing over here is a gas cloud. So this is two different telescopes giving us different information. This bright red dot is a gas cloud that we have named, because astronomers are great at naming things, B2. There is a B1 and a B3, but B2 is a particularly well-studied cloud. And the reason it's particularly well-studied is because it's one of these places that we have gone to look for amino acids. And this is a thing that we're trying to do because we're trying to figure out if the molecules that go into building DNA, which is what we require for living, are common in our galaxy or not. If they are common, then maybe it's easy to form life. If it's not common, then maybe it's hard to form life. So we've been looking for complex molecules. So primarily for these amino acids, but also we found a whole bunch of other complex molecules hanging out in this gas cloud, which is interesting. And of them, we have found ethanol, which is grain alcohol, also hand sanitizer and paint solvent, so not ideal, but it is grain alcohol. And then also ethyl formate. Ethyl formate is the smell of rum and the flavor of raspberries. So if we are on Earth, that is where we get our smell, that smell of rum, and the flavor of raspberries is from this ethyl formate molecule. So with those two, potentially delicious cocktail. You will not be surprised that my next slide is telling you about all the reasons you should not drink this. So there are some problematic molecules as well. It is the return of the hazardous waste sign. Formic acid. Formic acid will cause acid burns. It will damage your optic nerve if you are exposed to it. And it is involved in why ant and bee stings are so unpleasant. A lot of ant stings have formic acid in them. There are some creatures that have quite a lot of formic acid. Don't touch them. But yeah, they are corrosive. This is my new favorite sign. The divot in your hand is very, yep, got the point across. I will not touch that, thank you. Aside from formic acid, we also have formaldehyde, which is toxic. It's flammable at room temperature. It's corrosive, it's carcinogenic, and it's toxic. We use it as a preservative. Not so much anymore because of these reasons, but it was used as a preservative in museums for quite a long time. It suppresses your nervous system functioning. It's bad for you. Did my Google search history get a little weird when I was finding out what formaldehyde does to your body? Yeah. We also found methanol. This is another toxic flammable gas at room temperature. It's real bad for you. It digests into formaldehyde and formic acid, previously established to be no good. So this one I have rated just bad for you, 0 out of 10 stars. Also in this gas cloud is N-cyanide, which you can guess digests into cyanide, which kills you. It is super toxic. So our galactic cocktail that we have does have ethanol, which is our green alcohol. It has ethyl formate, which is our smell of rum and flavor of raspberries, but it also has formic acid, formaldehyde, methanol, cyanide. Don't drink it. It's very bad for you. So here's my takeaway. Space is filled with really strange things. Many of them will kill you. But sometimes we have to figure things out through really unusual pathways. So if before I explained the whole Neptune atmosphere thing to you all, saying, yeah, we learned about Neptune's diamond rain by using styrofoam, that would have made 0 sense. But we got there. It made sense. They thought it through in advance. They went, okay, we could do this. We'll try the experiment, see what happens. And it worked. And we tend to find out that most of the places are really, really bad for you. If you start looking into the rest of the solar system, it's not better. Every time you look at another planet in the solar system, it's just a death trap. We get aggressive sandpapering if you're Neptune, we get compression, or we just straight up, it's poison if you want to be upset about Mars. Mars is in the poison category. So those are the big things that I wanted to tell you about. I will remind you that I do have a new book that is not the one I just told you about, called 40 Ways to Know a Star. This is a less aggressively space will kill you book about the ways that the stars have taught us about the universe as a whole, and it is beautifully illustrated all the way through. But I will remind you of this book thank you for your attention and remind you to enjoy the Earth because it is the only nice one. Thank you.
Big thanks, and we have time for questions. If you'd like to ask a question, just come up to the microphone in the center.
As long as you are able.
I'll ask a question while we wait for other people to come up to the microphone, which is, Mars seems the least bad of the options of the other places to visit, but, what's so bad about Mars since we've got Mars enthusiasts?
Great. So Mars does seem the least bad, but that's a low bar because the moon has no atmosphere and is about 200 degrees Fahrenheit in daytime and minus 200 degrees in nighttime. So that's not great. Venus will just kill you. It's too hot and too pressured. Mars has an atmosphere. It's entirely carbon dioxide. It's not very thick. It won't protect you from UV radiation. And the dirt is filled with perchlorate, which is solid rocket booster material, and your thyroid loves to absorb it, rather than iodine, which you need. So the ground in, and you can absorb the perchlorate from the Mars dust by contact. So the Mars dust is literally poison, and if you grow things in dirt contaminated with perchlorate, which we have done, unfortunately, in areas contaminated by industrial pollution on Earth, where the perchlorate levels are much lower than that, you tend to preferentially pull your perchlorate poison into the leafy green material of your plants. So you can grow poison salad in your poison dirt on poison Mars. But yeah, it would be a bad time. Yes?
I'm guessing that we know what Neptune is made of from a few distant pictures that we got spectrum off of. How do we know what's deeper in?
So the deeper in terms of the rocky material, is that some of this is an estimation based on if we are going to create the right kind of density, we probably should have some rock in there. It is also going to our theories of how planets form, which is that if you throw gassy material and rocky material together, or in the early solar system, the rocky material will probably fall to the center of any object that is formed. So in terms of knowing the exact composition, we don't know the exact layers, but we have some information based on looking at the magnetic field of the planet, which tells us about there has to be layers that are conductive inside the planet. And so that limits us in some ways. It can't be rocky all the way out and then a thin layer of gas at the top. And then there are other things that we've gotten from spectra, as you say, from looking either from here or from close up. So a lot of it is modeling from what we've seen and then what we expect and then trying to make those match together. But there are different models. This is just my favorite. Yes?
Yes, in the case of Neptune with the diamond rain, would the carbon be locked in the diamonds that are deposited? And assuming that's the case, do we have any estimate of when that started and how long it can go on?
That's a good question. So in principle, yes, it should be locked into the carbon because diamond is a relatively stable crystal structure. So I don't see any reason why it should disintegrate or evaporate in any kind of way. And so yes, it should over time be draining the methane out. In terms of how long that could go, I really don't know. My expectation would be that the rate of diamond formation would just slow down with time. Like as you lose methane, you would lose your ability to do this. It would happen more slowly. But my guess is that it would probably have begun as the planet formed, and it will just sort of taper off with time. But considering that we see quite a lot of methane in the atmosphere now anyways, it probably still has quite a ways to go before it depletes itself of methane. Yeah.
That was a very good presentation about the diamonds and stuff. Enjoyed that. And mine actually kind of follows up on that, I guess. When you were talking about a diamond rain, then it became like, does it compress into like one big like sedimentary layer of diamonds within Neptune? And is it like, does Uranus have the same kind of atmosphere as Neptune? Would it be doing the same kind of thing?
So I think the sedimentary layer of diamond is what they're getting at with this diamond layer question mark. So maybe is the answer. I don't know if we have a clean expectation of what happens when you rain diamonds down inside a planet for long enough, but it should stack at some point. The behavior of that might be a little interesting from a chemistry perspective, but yes, it should stack up at some point. In terms of whether Uranus, would Neptune shrink? Probably not by a lot. No, I wouldn't expect it to. What it would change is the way that density changes with distance from the center of the planet. So the outer layers would probably get puffier and less dense, but the inner layers would get more dense. But on the whole, it would stay approximately the same, would be my guess. I'm mental mathing that. Did I get the whole question? Oh, Uranus probably is doing similar things. Uranus has some weird extra features because it's on its side and its magnetic field is really weird, but it is also, it does have methane in it, which is why it's kind of that blue-green color. So something like that could also very easily be happening on Uranus. Yeah. Yes?
You attributed the extra heat to diamond abrasion. Would the breaking down of the methane into its elements also release heat and cause some of that?
Oh, yeah, it might. I don't remember offhand whether that is a heat releasing or a heat absorbing reaction. Either is possible to my mind, because if you require high temperature to start with, then the temperature is available if you're going to be a heat sink. I would honestly guess that probably it is energy intensive, because otherwise we would have more diamonds falling out of like ethane and propane and all of those things a little bit more easily. But that is a guess. If it is energy productive, then yes, that could be another component to the heat. Yeah.
Advantage of the unoccupied microphone and ask another question. Because the farthest away you got was the center of the Milky Way, but I know most of your own work is on things outside of our galaxy. So are there good stories from your book that go beyond our galaxy?
There are many stories that go beyond our galaxy. I had particular fun talking about things that we have seen in other galaxies. There is a galaxy in a cluster that has a cadence to it. And so it creates these repeated pressure waves over time where it's accumulating material, and black holes are terrible at accumulating material. So what they tend to do is lose most of it into jets in two different directions. And this one has a cadence to it. And it seems to switch on and then off and on and back off. And so the people that were studying this particular black hole looked at this and went, oh, that's a pressure wave, which it is. It's pushing material with a repeated cadence. There's a frequency to this. And then they translated it into a musical note. And it was a B flat. So there was a black hole in a cluster of galaxies that is singing an incredibly low B flat, which I thought was quite fun.
So I am aware there's technologies, and I believe you would have applied it, where you can kind of approximate what chemicals and molecules are in atmospheres.
Yes.
So have there been any examples of planets with an Earth-like mass and radius that have unusually high concentrations of certain molecules or atoms?
We are actively looking for that. Earth-sized planets are remarkably difficult to find, because Earth, relative to our sun, is quite small. And so the ways that we see planets in other solar systems are most easily, or they're most successful with large planets and massive planets, which the Earth is neither. We do have quite a number now, but not a huge number, but like multiple dozens of Earth-sized or ish-sized exoplanets. Looking for their atmospheres and what's inside their atmospheres is an active field of study. There are press releases every other week, primarily coming from JWST, which this is one of its main mission goals, is to study the atmospheres of planets and hopefully to find ones like Earth that maybe have Earth-like atmospheres. So far, all we've found is no atmosphere, terrible atmosphere, terrible atmosphere, terrible atmosphere. So no luck yet, but it is an active thing that we're looking for, and people are studying this now. So if you start looking for it, you'll start to see people going, oh yeah, we found a new exoplanetary atmosphere. It's full of things you shouldn't breathe. That seems to be easier to do, to find the ones that you shouldn't breathe.
Okay, well, oh, go ahead. One more question.
Hello. I found like you guys looking for amino acids kind of like interesting to find life. I guess I was wondering why you guys maybe it was just in general, but you were like very specific on like looking at the center of the Milky Way. Like I was asking why did you guys decide to look there, and yeah, what went into that?
Yeah, that's a good question. So the reason that particular gas cloud is so studied is because it's quite dense. And the denser your gas, the more likely you are to have complex molecules. And so it's one of the denser clouds that we're aware of. And so it's kind of the best case scenario for finding these complex molecules. And so that's why we've chosen that one. There are other places we could go looking, but the more diffuse the gas is, the more likely it is to just be hydrogen and really simple molecules. So we want the dense ones, and that's just a particularly dense one. Yeah.
Thank you all again for coming, and let's thank Jillian again.
Thank you.